So today we're going to look at an old, and when I'm old I mean 50 years old. This is a Weston 1240 digital multimeter. Uses Nixie tubes. Couple of the neon lamps. There's no LEDs in this. This is neon lamps. Couple of the neon lamps for the positive and negative voltage are shot. We're going to fix that and check this thing out and see how accurate it is. I figured today, for something different, I'll show you this old Weston 1240. This is a Nixie tube voltmeter, and it's actually not bad. It's not off by far. Like, it's pretty darn close. If I put my 5-volt power supply, which is set for 5 volts right now, we'll see that it measures 0 because I didn't connect one of the probes. Might help. But there's a couple things that this thing needs to have done to it. Check the calibration on it for one, but so it's measuring 5.5 on the 200 volt scale, but on the 20 volt scale, as you can see, it's measuring 5.01, which is pretty darn close. What's my fluke say? We'll see what the fluke shows on this. Where it does have a problem though is measuring negative voltages because the light bulb burnt out. So my fluke is showing 5.02. That's certainly acceptable. On the 20 volt range it's a little bit off. We might be able to fix that. And on the 1000 volt range, well, it's off big time, but then again, you wouldn't be measuring 5 volts on the 1000 volt range. We're going to check this thing out and just see how accurate it is. I'll measure some known values and we'll take it apart and see what's inside it and see if I can get it to a little bit more accurate than it is. This is an AC powered unit, so I have to follow all AC powered equipment safety guidelines, like turning off the power. And it'll take 115 to 230 volts at 50, 60, or 400 hertz. 400 hertz. Oh, looks like there's some adjustments on the back here too for the calibration. So maybe I can just calibrate this without having to really dig into it too far. But let's just take it apart for the heck of it and see what's inside it. Don't do this. Those screws only have to be turned like 1 or 2 turns. I think that screw comes out. If you take the screw out, you're going to drop a lock piece off on the inside. Oh, maybe not. Something just dropped inside, so maybe that screw doesn't come out. I have to fix that now. Maybe I have to take the side panels off it and it'll open up. Take out the stand, maybe it slides out from the front. Is that what it does? Those screws don't appear to do anything. One thing I should point out is the first shop that I worked at when I was like 16, going to high school, the owner of the shop had one of these meters in his shop. But he broke it. That appears how it comes apart right there. Front comes off. Interesting. Interesting how this is constructed. Circuit board should lift out of here. What are all these things that fell out? I like the sound of that. The circuit board should lift out of this, here. What I got to do is that screw on the right, I got to turn it around 2 or 3 turns, because what it does is it locks the circuit board in place. But I haven't figured that out yet because I don't have a manual for one of these things, and quite frankly, this is the first one that I've ever taken apart. I've had this thing for a couple years, but it's just been sitting under the bench waiting for a day to look at it, and that day has come. Well, looks like that screw does hold it in place, but it doesn't have to come out all the way. It just has to be loosened off a bit. Looks like the board should lift out. It turns a cam that locks it in place. Okay, there's the main board. I'll have to put that other screw back in at the back here. It has a cam on it that locks the chassis in place. So let me just put that cam back in. I wonder what these came out of. So here's the circuit board. As you can see, the input connectors connect to 2 coaxial cables that are going into the chassis, as well as one that's not on a coaxial. So the volt, ohm, and common both have a coaxial line connecting it into the set itself. And the milliamp does not. They connect up to the board over to the main switch here and back down to the board over here. I'm not too worried about that. I don't think we have to worry about a problem there, but what we do have to do on this is the light for negative voltage is burned out. It fits in behind this little cover here. There's 2 lights in here, one for overload and one for negative voltage. It's in here. Or are they neon? Let's see what's in here. It could be neon bulbs for that matter. One of them's not working. Looks like they are neon bulbs. Or are they incandescent? That looks like a neon bulb, actually. What about this one? They both look to be neon bulbs. Interesting. It definitely looks like a neon bulb, and it's pretty black. We'll fire this thing up with it apart. Got to watch out for the high voltage over here, because there's a little transformer on this unit to step the voltage up. These Nixie tubes need about 170 volts or so to operate, so these operate at high voltage. There's a couple of neon bulbs here. I just wonder what this is for. One's for plus, and the other one's for minus, I believe. And then there's one for overload. I think that's how it is. This is the negative one here. And these neon bulbs look pretty, I think they're neon. They look pretty black. And then there's another what is that? Okay, one's overload. That's this one. And yeah, they're neon bulbs. You can see them, right? If we take a close look. It's a neon NE2. These are both NE2 bulbs. And basically what they do is they, here's a big one. This is for the 1 digit over here. This is a really tall neon bulb. But what these do is they light up this indicator, which indicates if you're beyond range, positive and negative. And then this one here activates as the number 1 digit. So this is what they call a 3.5 digit. So we got to make sure that these leads are not shorting. But these bulbs here, I think, are both toast. We'll power this unit up just to show what it does. Get the power cord. I got the power off now. Oh, wait a minute. It might not power up. Well, it should. It should power up. The switch is over here. I won't be able to measure anything because of where the hell is this on the bottom? Well, this is the different modes. That's how it selects the different modes. Right? It just, if you look down here, these copper springs make contact on the circuit board here to select the different modes. When you select milliamp or volt AC, volt DC, etc., these just make contact with these contacts on the board. So I don't know what to expect when I power this thing up. None of them are going to make contact. It should light up, I think. Oh, gotta find where I hook up my power, because the power pins are actually disconnected when you remove the back. The power cord, you can't power it up unless you put it together. Interesting. Obviously, they're going to connect to the back there and to this terminal here. One of them is ground and one of them is power. Don't know which one's which. I guess I can find out pretty quick. We'll just measure it. See which one's which. So 2 outside ones. The 2 outside pins have got power, so it'd be that one and this one. These are the 2 power connectors, the 2 power pins. This one here, ground. I believe I've got some NE2 bulbs that I could certainly replace these with. The ones I have might be a little bit bigger, but they would work. I'm just going to put the cover back on here now. There's something that's just cool about neon displays. Now I have 2 Nixie clocks that I built, a 6-digit one that I paid a lot of money for, and a 4-digit one that was actually quite reasonable. I think it was like $50. Got that one off of Tindy.com if you want to buy one. There's one guy's name the seller's name is Rob G. It's like $49, 4-digit Nixie tube clock. Kind of cool. I also have a Panoplex display clock, which is an old Heathkit, which again uses these display panels. It's a 7-segment display, but it still takes about 170 volts. The Nixie tube are actually 10 segments. They have individual anodes for each numeral, as opposed to a 7-segment display.
Not as easy as it looks. I have to get this into position and slide it down with the bulb already inside, and then bring it down, and then put the 1 digit in place, and now separate these wires so that they're not shorting out. Yeah, that should do that. We'll get another couple of bulbs. I think I've got some. I'm pretty sure I've got a couple of NE2 bulbs that I can replace. We'll just see if they're working first of all. Gotta figure out a way to turn this thing on. Okay, if I give it power, I've got it set for like, my power's probably set for like 11 volts now. I've got the front face on. I've got it connected to power. As you see, this neon bulb lights up. This is for positive voltage, and if I switch the input around to negative, the other one should light up. And it is, but it's very, very, very dim. I don't know if you can see it, but you can probably see the reflection there. This is for the negative. There you go. You see, it's so dim that we really can't see it. Pretty sure I've got two NE2 bulbs. We'll replace those NE2 bulbs so that the positive and negative display on this vintage meter works. And it actually is fairly accurate. I don't think I really need to even do much as far as calibration goes, because it is fairly accurate. Like it's within like a 0.2, 0.1, 0.2 of a volt, at least on the lower voltages it is. We'll check it out on AC once I'm done. Well, I found a couple of them in my old junk drawer. One of them, unfortunately, got one of the leads snapped off. I'm going to try and stick a new lead on this and see if I can salvage this one, because I don't have a lot of NE2 bulbs remaining in my collection. I like to try and get some use out of this one if I can make it work. So I'm just going to wait for my iron to heat up, and I'll try to stick some very fine wire on, and maybe we'll make this one the negative light. I can tack it on in place of the burned out negative bulb. That is how you do it. That should work. We're going to put this one in place of the negative light, which is that one. So I'm basically just going to cut this one out of the circuit, stick the new one on it, splice the wires, and we'll check this one, and that'll do the same for the other one. These bulbs should fit in here. It's a little bigger, but it'll still fit. And I'll stick it in like that, and maybe put some glue in there or something to hold it in place. But anyway, that should do the job. I'll just get this out of the way here so that the switches are not going to get damaged. We'll nip the old bulb out that's shot. We'll just cut it off right close to the bulb itself, because the bulb itself is shot anyway. So take this heat shrink tubing a bit back. Same with this one. Just take off the bit at the top. I tell you, the trouble I will go to save that bulb with the broken lead. Problem is this copper wire hasn't been soldered in so long, it doesn't want to stick to it. To clean it first. There's lots of heat into that wire to get that wire to actually accept the solder.
And yes, I am pronouncing solder correctly. Those of you that say it's solder, that's the American way. I'm not American. I don't talk like an American. I say it the correct way, pronouncing the L. I actually got ripped a new one when I was in high school because my electronics teacher was also an English teacher, and I used to call it solder. And he gave me a lower grade because I didn't pronounce it correctly. He was an old, miserable British guy, and if you pronounced words the wrong way, he let you know about it. He would make us pronounce aluminum, aluminum. Not quite the same way that the Brits say it, but close.
Okay, this is the negative lead soldered up. When I turn on, I've got it connected to display 11.2 volts negative, and it's lighting up, and the negative is nice and bright on the front. So let's do the same for the positive. That'll be easier because I don't have a broken bulb to deal with. So same as before, I'll just cut the old bulb out. And then when I put this back in, I'm going to, I'll put probably some hot glue on here or something to hold them in place, because they're never going to have to ever be changed again. This meter's not going to see enough service to have the bulbs burning out again. When this was in service, this was probably running day and night at a shop. Be careful with these leads that they don't break, because they're very, very fragile. I'll tin them first.
These bulbs have been sitting around so long that the copper has all oxidated, so I got to get them real hot to burn through that oxidation so that the solder will actually stick.
I'll tin the other leads that are sticking up here. Okay, other light bulb in place. Just got to hook up these two wires to it. Bend them out of the way a bit here. Bend these ones down a bit without breaking them, because we know how fragile these wires can be, right? Okay, those are both soldered on. Let's just check to make sure that they both work. And then I'll throw some hot snot on them to hold them in place. Okay, we should see the negative light light up first, which is the bottom one. And then I'll switch the connection around. So there's the bottom one lighting up. And now we'll switch the polarity around. And we'll see the top light light up. So there we go. Now they're working. So now I know that both of them work. Let's get some hot glue on there to hold these in place and keep the wires and stuff from moving, and then I can put this thing back together. We'll just stick some hot glue onto both of those bulbs to hold them in place. There. That's all that's needed. And that'll hold them in place once it dries, protect anything from shorting out the wires, and keep the bulbs from moving so that they'll light up the appropriate portion of the display. And you guys have a good look at this before I put it together. Discrete components. Gotta like it. Lots of Motorola chips in this one. These are all Motorola. The unit probably could use a good calibration, but I have no means to verify for calibration the unit itself. From my measurements that I've done, it's pretty close. Probably as accurate as this unit ever was, because when they first came out, they weren't as accurate as DVMs are today. Right? The Fluke set the standard, but prior to that, you know, if you were accurate within half a volt or so, you were still miles ahead of any of the analog meters of the day. So they still did a relatively good job. They were far more accurate than anything else that we had of this time frame compared to the analog VOM meters and VTVMs, which you had to kind of guess. You had to kind of read between the markers on the meter to guess where your reading was. This gave you a digital readout. So it's fairly accurate from the testing that I've done on AC and DC volts. It's fairly close to what my Fluke shows. We'll look at that in a minute. I'm just going to put the unit back together. You see it's a double-sided board, all an entirely plated and soldered board. Here's how these switches work on the bottom. If we look at the switches, when the switches are engaged, they close like that. They close all these terminals together. That one closes those ones. That one closes those ones. So they close like 5 terminals together. I think these are all independent switches actually. I think these are not all barred together. These are insulated in plastic. So I'm pretty sure it's like closing 3 separate switches at the same time. We can verify that with the meter. So these are together, but that's not, see? So these two get closed together, and these two, but not all 3. They're not all together. This is 3 separate switches. And that's 3 separate switches, as is these ones. So when you switch to different modes, it closes the 3 separate switches at a time. So what I'll do now is I'll slide this into the cabinet. And then these screws on the back, they just lock. I think they came out of the front here. They were in here. This is what, yeah, they fit inside here to give the switch its detentation. You see, they ride along, these 2 pieces ride along inside there on that switch, and the springs push them back. That's what these do. These sit in here, and these springs push these switches in, these ball bearings in. That's what makes the switch click. So I got to put those back together too. Oops. Those sit like that, and then that sits in there like that, so that they give this thing its click. Like that. On the back, we just tighten up the lock screws, and they'll automatically lock the circuit board in place. So basically you just undo these like 1 or 2 turns and it releases the circuit board. Got the handle to go back on it. Put that on. So now we can give this thing a test. I must have shorted, when I pushed it back together, my Nixie tube must have shifted slightly and shorted 2 of the leads together. As you can see, there's a double segment. We'll have to pull it apart to sort that out, because the 5 and the 0 are coming on at the same time. So let's fix that. Just release the catches on the back, and if I don't pull the knob off, it should pull the whole board out with it. Just going to reseat this tube a bit, make sure there's nothing shorting on it. Okay, I just reseated the tube by unplugging it and plugging it back in. I just want to see now if I fire it up whether the 5 and the 0 light up at the same time. I'm just going to power it up. Looks like they're still firing at the same time. Maybe the driver chip has got a problem. These are fired with separate cathodes, so it's like there's a short between the 5 and the 0. It could be internal in the tube, or it could be one of the drive ICs that's got a problem. It's likely this chip that's bad here. This U6B996079X. This is the Nixie tube driver chip for the 1s unit. I don't see any shorts anywhere on the board, either where I worked or anywhere else. There's nothing touching anything, so I don't know why it's doing that, but it is. When a 5 is displayed, it's also displaying a 0 and vice versa. You can see both segments come on. But I don't see any short circuits anywhere. There's no solder splashes or anything, or any dirt that I can see causing a bridge on any of these circuits. As you can see, everything's clear. Like there's nothing touching anything. And when I was testing it with the front panel here before, well, these contacts here aren't anywhere near. Like there's some bare contacts here on the board, but as you can see, they're not anywhere near it. So when it's sitting in there, when I had it operating, it was sitting in there like that, but nothing can touch because of the way it's locked in. In order to turn it on, right, the board is locked into a channel on the front here, so there's no way that it could short out anything. Put that back together, we'll tighten down the lock screws, and then I'll plug it in and we'll run some tests through it. This thing could actually run off of a battery pack at 1.2, and guaranteed that that battery pack would have 200 volts or 160 volts or whatever the Nixie tubes required, because this is not going to have any type of voltage inverter in it at all. It would be the battery pack would have a whole bunch of batteries in it to give you the power for the display. Probably a bunch of 22 volt batteries. They used to make 22 volt batteries at one time for tube radios. Either that or a bunch of 9 volt batteries, but I bet they were the 22 and a half volt cells that they used to make. Okay, let's power this thing back up. Now it's working. What the? Okay, So I don't know what I did. It's working. It's working. Let's just check the voltage out here and see whether we're accurate. So I'm feeding it 11.2 volts and it's showing 11.26. We can confirm that with the fluke. Let's see what the fluke says. If it's accurate, it'll be a fluke. Or is it? It'll be a fluke if it's accurate. One way or the other. If it's accurate, it's a fluke. Or it's a fluke if it's accurate. You be the judge. I'll clip this onto the same. So 11.26, 11.27. Yeah, it's good. It's close. As you can see, the display is now working. Let's go to 12 volts. My power supply says 11.9. Okay, my power supply now says 12.0. And this has got measuring. I'll just take it right to 12.0. 11.9, there's 12.0. So on my power supply, it's showing 12.0. I'm getting 12.04, 12.03. Positive. New bulb. If I reverse the power supply, negative. I like it. Looks cool. I might actually use this as a voltmeter. I got to get some new probes. The ones that I'm using are actually the ones I stole off my ESR meter because the ones on the fluke won't plug into them. These are protected type. Right? These ones are the protected type of high voltage boot covered probe, whereas this one here has just got a metal pin, and of course these ones here you get a shock if the probe fell out of the meter and you had high voltage on there, you could get a shock. So the new ones are a little safer. But there we go. Negative 12.05 volts. We'll switch it back to the positive side again. Plus, let's just check some more voltage. Let's crank this up. This only goes to 20, and then I got to switch to another range. So let's take this up to, oh, I don't know. Let's take it up to like 16.7 volts, 16.8. 16.7, there we go. 16.78 and 16.81. Close enough. Now I've gone over. Now you see what's happened now. I'm actually at 23.9. This is showing 3.89, so close enough, but this is flashing here because I'm over range, so I switched to the next range, 23 point. Okay, it's off by a couple volts on that range. How about the 1000 volt range? So that one's way off. Again, you normally would not be measuring, you'd be in this range here. So according to my power supply, it's 24 volts. According to my fluke, it's 24.1, and according to this, it's 24.6. We're still within a half a volt, and that would be considered, I think, on a unit of this age, even when this was new, it was probably only accurate within a half a volt. Again, much more accurate still than an analog meter of the day. I can take this up to as high as, I think this meter, this only goes up to like 32.1. There we go, 32.1, and this one's measuring 32.5. Not too bad, not too bad. We'll go down to below 1 volt, or below 2 volts. We'll see how it looks. So here's the 2 volt range, 1.58. 1.59. So here's the fluke, 1.592. This one's 1.598. I like the one. The one is just one great big NE2 bulb, but an extra tall NE2 bulb to make up the 1 digit. I like it. And if we go down below 1 volt, let's see how accurate it is here. So 0.3, This is millivolts, remember? So 25 millivolts. Well, it's pretty close. We'll go to 100 millivolts here. Okay, 0.186. 186.2 millivolts. That looks pretty accurate to me. I think that's a pass. Let's try it out for AC voltage. I'm on the AC scale. I'm just going to stick my probes in over here to the AC socket and try not to short myself out because I've got some bare wires here. So if you hear me scream, you'll know I got electrocuted. I'm trying to make these leads here. Let me grab an extension cord. Might make it a little easier to do it if I get an extension cord here so that I can plug both of these in at the same time and try and get a reading. $118.2 on the Variac. We'll take the Variac up as high as I can take it up. 150 volts. I don't want to leave that up there too long because there's actually stuff plugged into that Variac that I don't think I should probably be giving it 150 volts, if you know what I mean. I just thought about that. I've got some stuff plugged in there, like my TV, for example, and this will take it. But yeah, so it's working. It's working. AC voltage is also close enough. Let's check it out for resistance. Let's measure resistance. I've got 10.04K on the Fluke. Let's see how close this one is. It probably won't be. It'll probably measure 11 or 12. Oh, okay, 11.1. So it's off by 1K at 10K. Let's try a different value here. I just have a variable resistor, and I can't measure them at the same time because meters will affect each other. So I'll set it for like 18K. And then we'll look at the other one. This is on the 20K scale as well. So it's off by about 1K. Well, that's just to be expected considering something is this old. Let's try a lower value. We'll take it down to maybe 2.5. So 2.45. Oops. So that's looking a little bit better. We'll try a lower value now. Take it down to maybe 1.5, and I'll switch this down to the 2K range. So 1.56. I was measuring 1 point. Takes it a second to settle in. Three ohms. $200 ohm range. There it is, 3 ohms. So it's accurate on that range. $138 ohms. Let's test that on the 200 ohm range. So resistance wise, it's not as accurate, but voltage wise, AC and DC, it seems like it's doing the job. especially for a piece of technology that's as old as this is. So I think we're going to leave it at that. I think it's probably good enough. In order to calibrate this, I'd have to probably find a service manual for it and a calibration manual for it to calibrate the ohms scale. And it actually had a note on it that said resistance measures, I think it was reads high. I think it said resistance reads high. But anyway, AC and DC voltage, working great. Plus and minus indicator now working. So there it is, my old Weston 1240 Nixie tube DMM. Maybe we'll see this some more for voltage measurement. I'll put it on my bench and just use it as a voltmeter because we know that it does that and it's pretty accurate for measuring voltage. And it looks cool.